In this video lecture, I will introduce the concept of numerical integration and provide some motivation for studying this concept. And let's start with explaining what is numerical integration. And we're going to refer to the process of approximating a definite integral of some function as numerical integration. So numerical integration is finding approximately what this integral is equal to. And why do we need to be able to do such a thing? And the motivation comes from the field of statistics. And in statistics, we know that the probability is associated with the area. So if you're looking for a probability of some random variable obtaining certain values, you would look for the area under the what's called the probability density function. And for example, in probability, we can easily become interested in finding the following definite integral, and it will look something like this. Again, it's a very common probability density function in the field of probability or statistics. And for example, this particular integral may represent the probability of a standard normal random variable to fall in the interval between 0 and 1. And so we want to be able to find this value. And more interestingly is that, well, theoretically, one approach that we can take is we can try to find the antiderivative of this function and then just evaluate it from 0 to 1. Essentially, what we're doing here is we're trying to find an integral of this function, right? So more or less, this is what we are looking for. And what is the problem with trying to find an antiderivative of this function? Well, it does not exist and in closed form. So what does that mean? That means we cannot find a function that we can simply write using the definition f of x equals such and such, and therefore we cannot use the fundamental theorem of calculus. And that creates a problem. And why is it a problem? And this is a problem because in statistics, without even learning the concept of an integral, every introductory statistics course student will be able to tell you that this probability is equal to roughly 0.34 by what we call the empirical rule. So that kind of does create an issue because on one hand we know what the answer is, on the other hand we don't have a proper tool in calculus to address this problem, and this is where the numerical integration comes in. So the idea is that we actually don't need to know the exact value, and the empirical rule is pretty clear. It says, hey, this probability can be approximated. So it is not equal to 0.34, it's equal to 0.34 something something, which is approximately equal to this probability. So in many applications, we actually do not need to know the exact value of a definite integral. for the sake or for the purpose of the application, we can be satisfied with a certain approximation, with certain accuracy, depending on the application. And therefore, we are going to need the methods of numerical integration that we are about to learn. And the whole idea behind the numerical integration is very, very simple. We just need to go back and recall the definition of a definite integral. We define definite integral to be and maybe you want to pause here for a moment and ask yourself, how did we define a definite integral? And when you're ready, just unpause. But I'm going to continue and write the definition here. So the definite integral was defined as the limit as n approaches to infinity of the following expression, which we refer to as the Riemann sum. And here it is important to understand all the notation. We have some function here in mind. We have some interval in mind. We also have some n, which we get to choose, and n represents the number of intervals. So each n creates like a partition. And in this diagram, each of these intervals have the same length, which we label delta x. And delta x, we prefer it to be the same for all subintervals, but in theory it doesn't matter as long as the largest one eventually goes to 0. The integral will be the same. So, but again, it is nicer when if we had to choose between them all being the same and not, that we would prefer them all being the same. And each one of them would be or can be found using this formula. And in this notation we have also index I. I represents ith subinterval, which I'm gonna draw with using this notation, and we pick xi star from the ith interval. And we can, again, as long as the width of each interval goes eventually to 0, we can pick any such value, and it doesn't have to be the same rule for each sub intervals. And now in this picture, once we pick this xi star, now what does f of xi star represent? F of xi star represents the output of the function at this point. And remember, we're going to have many of these x stars, so here somewhere we can pick x1 star, and then f of x1 star will represent the output of the function at that point, and so on. And the last one will be xn star, and this line segment will represent the output of the function at that point. And finally, so what does this all represent? So this is not dx, sorry, this is delta x. And now xi, again, it's an arbitrary picked point. F of xi, it's the output of the function at that point. F of xi multiplied by delta x, what is that? Well, that now becomes the area of a rectangle with the base at the subinterval and the height equal to the output of the function at that point. And as you can imagine, when you have many of these intervals, the area of all of these rectangles, which is represented by this sigma, and again, sorry, this is not infinity, this is n. So this expression represents the area, this is the area of n rectangles, and the limit, the whole expression now represents the area under the curve on the interval from a to b. So this is how we defined the definite integral, and this is what all of these ingredients on the right side represent. Now, what are we going to do with this? We're actually going to kind of make a step backwards, right? So we're going to look at the integral from a to b of some function, and we're going to, again, this is a, I'm just going to copy the definition. And now we're going to acknowledge the following transition. When we on the right side we have a limit, then the two sides are equal. So the left hand side is equal to the right hand side. So now the question is, what will happen if we take the limit away from the right hand side? So clearly these two are not equal anymore, but what's the relation between the two? And it's kind of pretty obvious. The relation is that they're not equal, but they are approximately equal. And that's kind of it. That's the whole idea behind the numerical integration. We're gonna say, hey, when we need to compute a definite integral, which is on the left hand side of this statement, what we're going to do is we're going to pick some value of n, and then we're going to create a partition, and each partition will be made of n intervals like this. And on each of these intervals, we're going to have to do kind of the same thing that we've been doing. We're going to have to pick this xi star, arbitrary or not. That's a whole different conversation we will have. But the idea is for every n, we can do this. And then if we plug everything in here, we're going to get some finite sum. And we're going to therefore get the approximate value of a definite integral. And just to give you a heads up, if this is what kind of we're going to learn in the next 3 lessons, if we're going to choose this xi star, kind of like a representative of an interval, to always be the left end of the interval, we're going to end up with what's called the left end point approximations. If we're going to always pick the right point, we're going to end up with what's called the right end point approximation. Now, if we're going to pick always a middle point, so if we always pick the average of the two endpoints, well, you would guess this two would have the name midpoint approximation. Now, left end point, right end point, and midpoint approximations, they all use rectangles. So they're all based off the Riemann sums. So they all use areas of rectangles to approximate the area under the graph. However, we can change that up too. So it's going to require some development, but instead of rectangles, we can also use trapezoids. And we can also use parabolas. And if we abbreviate the left end point approximation with Ln and the right end point approximation with Rn, then the midpoint approximation will be, if you were to guess, you would probably call it Mn. And if we use trapezoids instead of rectangles, we would call it Tn. And if we're going to be using parabolas instead of trapezoids or rectangles, then for that we're going to have what's called a Simpson's rule, and we're going to call that Sn. So this is what's coming up next. This was kind of a brief introduction to the concept and the idea of numerical integration, along with some motivation.